Hi, today we're going to continue our discussion about vector-valued functions. And again, a vector-valued function is basically a way to describe the path of an object, on a plane or on a surface. And that's really what we're doing here. We're describing paths. Okay? How is the object moving? Where is it moving? And we're going to take a little bit more time with that today. So you might recall from the other day, yesterday, we said that in a vector-valued function, we have one independent variable. Recall from yesterday that when we are looking at a vector-valued function, in 2 dimensions, we use one independent variable, because that's really when you have as a function, any function like f of x is a function of y, right? There's one independent variable. But when we move to 2 dimensions, or 3 dimensions, three-dimensional space, then we start to have 2 dimensions, or 2 independent variables. And we're going to talk a lot about this. Now, there are a couple ways we can do this. One, if we have v of t, notice we're in 3 space, but there's only one we could have. I guess I should say we could have 2 independent variables. I guess they could have 2 independent variables. It's more specific. If there's one independent variable, it's just a trace. And that's what this is. If it's one independent variable, it's a trace. In other words, it's basically what a trace is imagine you have this toilet paper roll. Okay? The toilet paper roll of mathematics. Now this toilet paper roll is a cylinder. Okay? And let's say I take my pen of mathematics and I draw a line on it, going all the way around. Now you would say, Mr. Warner, that's a line. Yeah, I'm drawing a line on this toilet paper roll. And I go all the way around the toilet paper roll, all the way around, all the way around. Now this line is a trace. Somewhere on the cylinder, it's kind of like I took a plane and I cut it. That trace is that line on this toilet paper. In a vector or parametric form, we can represent that trace by using one independent variable, in this case, t. Now, sometimes, we're going to talk about this later on today too, we may want to look in 2 variables, so we use t and u. Well, this is not a trace. This would be a vector or parametric representation of the entire cylinder. So this is the parametric representation of the shape of the function, or surface, I guess fair to say, where this would be a trace, where in terms of t would be a trace on the surface. T and u would be the actual surface itself, because again, it's like x and y. You're adding an x and y component to it. Here we're only adding one component. It'd be like f of x. It's like a line. Y equals x. So before we can start writing these traces, though, let's kind of review domains and domains of vector-valued functions. We talked a little bit about this yesterday. Now, when we're talking about the domains, again, what we're really looking at is what is restricting our function. In this case, for our domains, they're going to be t's and u's. In this case, it's going to be t. So if we look at example number 1, I look at, well, what t can't be? Well, there's no restrictions. Only 2 things you really can't do: divide by negative and have negative under an even root. So in this case, t can be anything. So t will be an element of all real numbers. Look at number 2. Same idea. Well, I have a few more restrictions. For the x component, right? T, we have root 4 minus t. For the y component, we have t over 4, and for the z component, we have negative t. Well, which one of these is the most restrictive? And of course, it's the square root of 4 minus t. So we know that 4 minus t has to be greater than or equal to 0, or t is less than or equal to 4. You can write it this way, or you can even use our old interval notation, where 4 is a hard bracket. Like so. For question 1, we want to evaluate if possible, the vector-valued function. The key word there is a function. All function rules apply. for vectors. So I can just substitute in, and that's what we're going to do here. So if I'm looking for r of 1, I go up here, there's r, it's asking for question number 1. Everywhere there's a t, I let t equal 1. So this would become r of 1. We would get 1i, or just I, plus 2j, right, minus k. And you can write it in your vector valued function form, or you can use your chevrons. 1, just look at the coefficients, 1, 2, negative 1. And there we have it. Same thing, r of 2, r2, we can just plug that in. We would get 2i plus 4j minus 2k. And again, I can write it like this, or I can use my chevron form, 2, 4, negative 2. Either one's acceptable. R of s plus 1, everywhere there's a t, will a t equal s plus 1. So we would get r of s plus 1 would become s plus 1 I plus 2 times s plus 1 j minus s plus 1 k. And that's perfectly acceptable. You want to write in chevron form, s plus 1, I'll distribute here, 2s plus 2, distribute here, negative s minus 1. And very easy to do. So all our rules from functions have to apply because it's a vector valued function. And so let's take a quick look at some examples like how we can write in vector form. Remember, we want to write in vector form, or sometimes as a parametric, really it's a parametric, vector form because it describes the path. And that's really what we want to do. We want to describe the path. How are we moving along the curve? And we kind of talked about that here. Ready? If I were to walk around the toilet paper of mathematics, I will be walking in this path. That's that trace. Okay? So we have this parabola graphed on the xy axis. Now notice, this is not a three-dimensional surface because they are specifically telling us this is on the xy axis. So this is just on the plane on the only on the xy plane. In other words, this is going to be two-dimensional. And if it's two-dimensional, we know it's going to be z is 0, so we don't have to worry about the z coordinate. So it's two-dimensional only on the xy plane. So in other words, there's only going to be one independent variable. So to write this, I would just like you would back in 3-calc, let x be t, y would be t squared. There is no z because remember we're only on the xy plane, so it's very flat. Okay, so we would write our vector valued function. Now this is your parametric form, but as a vector valued function, r of t is something x in the I direction plus something y in the j direction. And we would get t, that's my x, and t squared over here. And that would be our vector valued function. So it's basically just more of an application, another way to write our parametrics as a vector. Because we've been talking about this for years now, for a few years, that a parametric is a vector. It gives us direction. From that direction, we can find the length of a vector. So, all right, the next one, this should look familiar to us. This is an ellipse on the xy plane. So again, this is a two-dimensional graph. This is only in 2 dimensions. So there's only one independent variable right here. And we're going to use t for that. Now, I could let x be t, solve for y, but that gets pretty nasty. So we're going to use a little bit of something that we learned from pre-cal a few years back, we reviewed last year in calculus, is that this is nothing more than we can use our circle. We can use our Pythagoreans. We know that cosine squared t plus sine squared of t equals 1. Now, I'm going to tell you a secret. I could have switched those. I could say sine squared plus cosine squared. You'll get the same answer. The only difference is, we talked about this yesterday in yesterday's video and notes, is that if you switch sine and cosine, all you do is you just change your direction. Right now, when we graph our ellipse, we're typically going in the counterclockwise rotation. But if I did sine squared plus cosine squared, it could either change where I start. Instead of starting at 0, I could change at the top. It just changes where I start. If I change one to sine, it changes my direction. We talked about that yesterday. But we're going to go by the traditional way, by letting x be for cosine, y be for sine. It does eliminate some confusion. So we know from pre-cal that then this is just going to become, x is going to become 3 cosine t, and y becomes 2 sine t. And if I were to write this as my vector valued function, we would get 3 cosine t I, put that in parentheses just to separate it out, plus 2 sine t j. Now again, what if we switch them around? I could have that. I could have 2 sine ti plus 2 cosine tj. That's just going to change our starting point, honestly. In some cases, if you make it negative signs, you can change your direction. But the next question I want to ask you is, what happens if it's not graphed on the z-axis? What if we said graph on z equals 2? Well, in that case, all we would do is we would add 2k. So this would be our ellipse raised up 2 units above the xy plane. And that's what that would look like right there. All right, number 3, this is y squared. Let's make that a plus z squared. One of these days I'm going to fix that. Graphed in 3D space. Now, once we get into 3D space, now they're telling us that this is a surface. Therefore, we need 2 independent variables. Remember, this is graphed in space. So what's happening here is, now I don't want just this trace, I want every part of it. Remember, this is like saying all x's, but now I need all the y's. So I'm going to need 2 variables, x's and y's. Thank you, toilet roll of mathematics. Right there. So first things first, let's take a look at the shape. This is a circle on the YZ plane. But in 3D space, this is a cylinder. And we can draw that cylinder. On the YZ plane, if I draw my circle, and it opens on the x-axis. So it goes down, like this. And there's our cylinder. So because this needs 2 independent variables, we're going to pick them as t and u. Sometimes you'll see books say u and v, and that's okay too. Most calculators, most technologies tend to use t and u. That's what I'm going to go and stick with here. All right, so if I were to write this one, I'm going to solve for one of the variables. Okay, actually, I'm not going to solve for one of them. I could solve for z and let z be t, or let y be t and solve for z in terms. Or I could use my Pythagorean again if I divide by 16. So I would get y squared over 16 plus z squared over 16 equals 1. Now, notice, we normally use cosine squared plus sine squared equals 1. But this time, because that's x and that's y. But this is where it gets a little more fun, I think, for some people. I'm still going to let y be my sine. So I'm going to say y equals 4 sine t. But for my z, I'm going to let z be my cosine this time. It doesn't really matter. I could treat it the same. Because it just really depends on where I start. And I'm going to make a full circle anyways. So I'm going to let z be for my cosine. So z would be 4 cosine t. Now, both of these have to be in terms of t because they depend on each other. The cylinder depends on that. So the y and d really depend on t right here. However, what variable doesn't depend on t? Or depend on this? That's x. There's no x, so remember, x can be anything it wants. So we're going to let x be u. So it's independent. So that's what this basically says. U is independent of y and z. And so it can be anything it wants. So writing our vector valued function, r of, and we're going to use t tu, this time tu equals, in the x component, 4 sine of t I, 4t I, plus 4 cosine t j, plus u k. Whoops, I messed up. Sorry. I let x be u, so that should be ui plus 4 sine tj plus, and in k, sorry about that, 4 cosine t k. There we go. And there's a lot of different ways you can actually kind of write these answers out. But anyway, sorry about the mistake there at the end. I hope you guys enjoyed the video, and I will see you guys later. Bye-bye.